What happens when something dissolves in water? Well, we have a variety of different forces here. We're going to look at sodium chloride, table salt, dissolving in water. Sodium chloride is a solid at room temperature because there are these attractive forces between the positive ions and the negative ions. We call them ionic bonds. That's a strong force, right? Solute attraction. Water is a liquid at room temperature. It is attracted to other water molecules by hydrogen bonding, along with dispersion forces and dipole-dipole forces. In order to get these two substances to mix, we have to have some attractive forces between the water molecules and the ions in the ionic compound. Water is a polar molecule. The negative pole of water will be attracted to the positive sodium ion. The positive end of water will be attracted to the negative chloride ion. And so when we have a balance between the strength of the solvent-solvent, solute-solute, and solute-solvent attractions, then everything will mix together and we can make a solution. If one of these forces is much stronger than the other, then they will not mix together. So many ionic compounds dissolve in water, but not all of them. We talked about solubility rules back when we talked about precipitation reactions. Things like calcium carbonate don't dissolve in water. Calcium carbonate is one of the components of that rusty hard water scale that builds up on the faucets and things. Calcium carbonate is an ionic compound, but it doesn't dissolve in water because the attractions between the calcium ions and the carbonate ions are too strong. And it would rather stick to itself than get involved with water. That's not something that you can predict at this level of knowledge. There are some elaborate theories that do explain all of that, but we're not even going to go there. So here's the sodium chloride chunk. It's really just one large crystalline solid with sodium chloride. What happens is the water molecules come up to the sodium chloride, and I mean, in one way you can think of water as being sort of a two-faced friend, right? He can be friends with you, and he can be friends with your enemy, just depending on what face you're seeing. So here, water's going to send his positive face towards the chloride ions, the negative. And so the water molecules will come and show their positive side to chloride and say, hey, come on out, come out and play with us. Oh, I don't want to leave my sodium, I'm so attracted to that. Oh, but we're positive too. And it takes more than one water molecule because it doesn't have a full +1 charge, it's got a partial charge. It takes a bunch of them, but they can surround this chloride, and all of these attractions between the chloride and the water replace the attraction that the chloride was experiencing to the sodium atoms, sodium ions in the crystal. The water can turn its negative side towards sodium and do the same thing. Surround the sodium ion with partial negative charges that offset the forces of attraction that the sodium ion had for the chloride ions in the crystal. And so this is how water acts as a solvent for ionic compounds. Any questions? It's all about the charges. So when we put sodium chloride in water, sodium chloride is nicely ordered. If you look carefully at salt crystals, they're little cubes, aren't they? They don't do that at the salt-making plant. They don't form them all into little cubes. Sodium chloride naturally does that. You break it into small pieces, and it's little crystals like that. You put that in water, the ions are going to separate. They're going to mix around. They're not just going to sit in a lump on the bottom. They're going to mix around and form a homogeneous mixture, which we call a solution. If you keep adding sodium chloride to water, will it keep dissolving? No, eventually you'll get to the point where you can't dissolve any more sodium chloride. And different substances have different levels of solubility, different amounts that you could put in a beaker of water and have them dissolve. So solubility is a concept that measures how much of a compound will dissolve in a certain amount of a solvent or a liquid. So we usually measure that in grams per 100 grams or something like that. So the solubility of sodium chloride, 36 grams of sodium chloride will dissolve in 100 grams of water. If you add a little more, if you've got 36.5 grams of sodium chloride in 100 grams of water, that extra half a gram will not dissolve. It will just sit on the bottom. So at 36 grams of sodium chloride per 100 grams, we say that is a saturated solution, meaning you can't put any more solute in. It won't dissolve. The water is full of sodium chloride. It can't take any more. Yes?
So you're saying that if you use a brine solution that's higher than that, you're wasting salt, basically?
Yeah, you cannot make a solution at room temperature that contains more than 36 grams of sodium chloride per 100 grams of water. That's the maximum you can make. If you add more, it'll just sit in the bottom.
And if you heat it and then bring it back down to room temperature, will it come out of solution?
Yes. If you heat a solution, the solubility is dependent on temperature. So if you heat it up, more will dissolve. And we will talk about a supersaturated solution, but most things, as it cools down, you'll see it begin to precipitate out. So saturated means it's full. If you think about a sponge that's saturated with water, what if you put more water into it? Water's going to drip out, right? It can't hold any more. Sometimes we get rain here, and the ground gets saturated. When that happens, the extra rain that falls can't sink in, and it runs off, and you can get some flash flooding happening. So saturated means it's got the maximum amount. If you have less than that, it's unsaturated. And you could put more in. You could put more solute in, and it would dissolve. Supersaturated seems impossible. Supersaturated solution is one that holds more than the normal maximum amount of solute. This will normally precipitate as it cools down. But sometimes you can form a supersaturated solution. It's not very stable though, and it will precipitate out. Another supersaturated solution is in an unopened soda can. There's always a little bit of airspace above soda in a can or in a 2-liter bottle, and that is pressurized with carbon dioxide. So they have forced carbon dioxide into the soda. When you release the pressure, then what happens? It bubbles, right? You see the bubbles coming up, that's the carbon dioxide coming out of solution, and it will just keep doing that until it reaches equilibrium. So here are pictures. It's not nearly as fun as the video. Looks like water. You disturb it, and it forms crystals very rapidly, and it gets warm. Or did it get cold? Oh, it got warm. And then you can actually tip this upside down. Yeah. So the solubility rules that we studied earlier give us qualitative descriptions. You know, this one will dissolve in water, this one won't. And that's really useful. But molecular solids can also dissolve in water, and it depends on whether the solid is polar or not. Table sugar is polar, and so it is very soluble in water. But nonpolar things like lard, vegetable shortening, cooking oil, motor oil, those sorts of things are not soluble in water because they are nonpolar. And so the interactions between the water molecules are stronger than the interactions between the solute and the water, and it will not dissolve. Electrolyte solutions. Now, you hear the word electrolyte. What popular drink has electrolytes in it? Gatorade, right? Electrolytes are ionic compounds that dissolve in water. Your body needs a certain amount of salts, and not just sodium and chloride. It needs potassium and a little magnesium and some other things as well. These are called electrolyte solutions. They conduct electricity. The charged particles in the solution allow electricity to pass. Non-electrolyte solutions contain dissolved molecules which are neutral and do not conduct electricity. So if you make a solution of sugar in water, it will not conduct electricity. Here we have a picture of what sodium chloride does. It separates into charged ions. Sugar, you have individual molecules of sugar. There's no charges involved. Solubility varies with temperature. Generally, solubility increases with increasing temperature, but there are some substances that actually become less soluble at high temperature. We see that the solubility of sodium chloride depends only a little bit on temperature. But things like potassium nitrate, it depends a great deal on temperature. At a higher temperature, it's very, very soluble. At, what is that? About 55 degrees, you can dissolve 100 grams of potassium nitrate in 100 grams of water. Equal amounts. It's kind of trippy to see because usually you can only put a little bit into water, but potassium nitrate is very soluble. Calcium chloride, very soluble. It'll do that at almost room temperature. Equal amounts. So, you know, these are examples of solutions where you can get maybe 150 grams of solid dissolved in 100 grams of water. So the solute actually has more mass than the solvent, but we would often still call water the solvent. One way we purify solids is a technique called recrystallization. And in this process, you take your solid, maybe that you made in the lab, and you dissolve it in a solvent, and you make a saturated solution at an elevated temperature, and then you let it cool down slowly. And as you let it cool down slowly, crystals will form. When the crystals can form slowly, they tend to exclude other substances. So any of the impurities will get excluded, and you'll get a much purer crystal.
Is that what you did with the potassium?
Pardon me?
Is that what you did with the potassium?
No.
Sorry, the aluminum.
Yeah, with the alum, we let it cool slowly, and a lot of you got some really big crystals. Those of you that didn't get the big crystals got little tiny crystals because they formed quickly when you put the beaker on ice, right? They form suddenly. Rock candy is just made with a heated solution of sugar. You put a string or a wire in there and you let it cool down slowly, and it grows these beautiful sugar crystals. And that sugar is going to be quite pure because they're going to line up in just the right way. Oh, yeah, there we go. So rock candy, you know, that's something you can try at home. You have to make sure that you make that initial solution saturated at an elevated temperature. So hot water, and add tons and tons and tons of sugar until no more will dissolve. And then hang a string in there and let it cool. Leave it alone. You'll cover it so flies don't get in there. But as it cools, you'll form these beautiful sugar crystals.
So when you do something like that, will it reject, it doesn't reject food coloring, right? I've seen it in different colors, but will it reject flavor? Like if you try to put some vanilla or?
That's a good question. In theory, it should reject food coloring and flavoring and such. And so, you know, I was just thinking of that in the back of my head because you see the colored sugar crystals, rock candy, and I'm not sure exactly what's going on with those.